In this video, I'm going to show you how to train a convolutional neural network using PyTorch. Let's see what is the recipe of training a CNN. The first step of this recipe is to import packages. The second step is to prepare the dataset. The third step is to build a CNN. The fourth step of this recipe is to instantiate the model. Fifth step is to create a loss function and optimizer. Step 6 is to train the network. In order to train the network, we need a forward pass. Then calculate loss. Then calculate gradients. And finally, update the weights based on the computed gradients. You can also validate the model. The seventh step is to plot the training and validation loss. The final step is to plot the training and validation accuracy. Now let's dive in the code. We're going to use Collaboratory or Collab for short so that you can write and execute Python in your browser. So now it's time to implement all these steps together into code. Go to the Google homepage and type Collab. Then click on the first link and you will be redirected to the Collab page. Go over to the left side and click on File. Then click on New Notebook. Rename the file name. At first, we need to install the Torch and Torch Vision. pip3 install Torch, then Torch Vision. We have to set up the runtime for GPU. To do so, click on Runtime, then choose Change Runtime Type and select GPU option from Hardware Acceleration and click on Save. To run this block of code, click on the circle on the left side. Now we will move on our first step. In order to be able to use datasets and build a network in PyTorch, we need to use in PyTorch friendly format so that the framework will understand the format. Let's see how we can achieve it. Firstly, we need to do some imports. We import Torch and Torch Vision. We import torch.nn.functional. We also import torch.nn. We import torch.optim. Optim package deals with optimizer. From Torch Vision submodule, we import torchvision.transforms. Transforms package deals with dataset. For plotting the loss and accuracy graph, we also import matplotlib.pyplot. Let's move on the second step. Firstly, we define a transformation of images using transforms. Transforms are common image transformation. They can be chained together using compose. We use resize to resize the input image to the given size. In this case, 28 by 28. We use toTensor for converting images to the corresponding tensors. We also use normalize to normalize the tensor image with mean and standard deviation. In this case, the mean is 0.1307 and the standard deviation is 0.3081. The next thing is to accumulate the dataset together. MNIST comes as the part of torchvision.datasets. We decide to get the dataset in folder. In this case is data/MNIST. For training, we set train flag to true, and for testing, we set train flag to false. We set the download flag to true for both cases. We tell the PyTorch that if the training and test datasets are not in the particular folder, then download and put in that folder. Finally, we set transform to transform, which is previously defined. We build train loader and test loader getting the data ready for PyTorch. torch.utils.data.dataloader class is the heart of PyTorch data loading utility. The first argument of dataloader object is the dataset. Then we decide the size of the mini batch. Our dataset is too large to use entirely, that's why we use randomly sampled 32 images in each iteration. Random part comes from shuffle flag. Now it's time to execute this block of code. If you would like to get tutorial regarding deep learning, please subscribe my channel. Let's move on the third step. We are going to build this CNN which has two convolutional layers, two pooling layers and two fully connected layers. And the last fully connected layer is with dropout. It is important to know how to calculate the size of the output tensor of convolutional and pooling layer. For this CNN, the output tensor of the first conv layer is 24 by 24, which is the input of the first pooling layer. If you don't familiar with calculating the output tensor size of conv and pooling layer, please visit the link dropped in the first comment. We first build a class called net which inherits from nn.module. Then we start the init method where we pass the number of class as argument, in this case 10. We call the superclass using super operator, then we declare all the parameters we have. The number of channels for convolution filters is arbitrary. With experience you will get the better options. Now we create conv on layer. The first argument is in channel, in this case 1. We set the out channels argument as 20 and kernel size 5, stride 1, padding 0. Similarly, we create conv2 layer. In this case, we must have to set in channel as 20 because previously we set out channels 20 for conv on layer. We are not going to create pooling layer here. We will use pooling layer later in the forward method. Now we are going to create the first fully connected layer. The first argument is the size of the input feature, and in this case 4 times 4 times 50. And the second argument is the size of the output feature, and in this case 500. Then we create the dropout layer. Dropout is an effective technique for regularization and preventing the co-adaptation. The argument is the probability of an element to be zeroed. We are using 0.5 in this case. After that, we create the last fully connected layer, and of course the size of the output feature would be the number of class of the dataset, and in this case 10. Now we have to implement the forward method. We start by passing our input image to conv1, followed by ReLU nonlinearity and a max pooling layer. Then we continue with the second convolutional and pooling layers. The arguments of the pooling layers are the input x, kernel size and stride. Now the output of the pooling layer will be fed in the first fully connected layer. To do so, we need to reshape the tensor. We reshape the x by using view function. Then we continue to pass the input x to the ReLU nonlinearity, dropout and the last fully connected layer. Finally, we return the output x. We will use GPU, so we have to enable the GPU acceleration. We create the object device for using GPU. We are very close to train the CNN. Now let's jump into the step 4. In this step, we instantiate the model. After that, run this block of code. In step 5, we create a loss function and optimizer. In this case, we instantiate the cross entropy loss and Adam optimizer. Here we do the training. We would like to keep track the loss and accuracy. Then we loop 20 times over the entire dataset. We move the training data to the GPU. The forward step is done using model inputs giving us the results. In this case, outputs. Then we compute the loss using our predefined loss function. After that, we compute the gradients using loss.backward command. We use zeroGrad function in order to not accumulate gradients from previous iteration. Finally, we change the weights using optimizer.step command. We compute the predictions using torch.max command and we update the loss and accuracy. Similarly, we test the model by feeding the test data. Finally, we calculate loss and accuracy for every epoch and we print out the epoch number, loss and accuracy during training. After 20 epochs, we can see that the training accuracy is 99.81% and the validation accuracy is 99.07%. In step 7, we plot the training and validation loss using matplotlib.pyplot function. Similarly, in step 8, we plot the training and validation accuracy. If you have any question regarding this tutorial, please leave a comment below.